Hello everyone, in this video we will calculate the volume of a solid of revolution generated by two curves using the Washer method. So what is the Washer method? Washer method is an extension of the disk method. So in previous video we have learned how to use the disk method to calculate the volume of a solid. And one important factor about the disk method is the vertical or the horizontal elements is perpendicular to the axis of rotation. Okay, so the word perpendicular ties with the disk method. So Washer method applies the same concept. So what is the difference between the two? So why Washer method is an extension of the disk method? So let's go to our formula sheet. Okay, so on this formula sheet, I indicate to everyone that using the disk method, if we work with the axis of rotation as the x-axis, then our element should be the vertical element, and vertical element is perpendicular to this axis of rotation. Note the formulas here. You are going to square your function, okay, and then you integrate. So still the same as volume equal to pi. Integral from a to b, because a, b's are the values on the x-axis, your upper and your lower limit will be the x values, and you square your function, integrate your function in terms of x. Alright, so go to the Washer method that I indicate here for everyone. Do you see that you also have y square? Here you have y2 square, but subtract the y1 square. The rest is the same, right? Pi multiplied by integral from a to b. A and b are the upper and the lower limits of the x values on the x-axis. You integrate in terms of dx as well. Is also the vertical element, which is perpendicular to the x-axis. And x-axis is the axis of rotation. So in this case, you must square the function and subtract the other function, and y2 squared in this case is your upper function, and your y1 in this case is your lower function. So how do we recognize the upper and the lower function? Then we have to go back and review the concept of finding the area. In order for us to work with the upper and the lower function, you need to identify the area that you are working with. Okay, so I have a function here, okay, y2, and another function y1. So you need to shade in the area that you are working with. Okay, place your eyes within this area to recognize which one is the upper and which one is the lower. So the easiest way is to draw the element. In this case, is perpendicular to the x-axis, right? And the vertical element in this case. So with the vertical element, take a look at this. This should be your upper function y2, and this should be your lower function y1. Okay, so using the Washer method, we have to apply the understanding of the finding the area and also the disk method and applied it to the Washer method. So let's get back to our lesson. So in here, in this document, I stated all the steps for everyone, very much similar to the disk method, but this is the Washer method, and we are dealing with two curves, okay? Because we are dealing with two curves, so we have to square the upper curves, subtract the square of the lower curve. Before I get into the formulas and explain a little bit more for everyone, I would like to mention that if I say Washer method, it's the same thing as they say method of rings. In some textbook, the author would say the method of ring, and some textbook would say the Washer method, and they both are the same. Okay, so why do they say it's the method of ring? Because sometimes it's referred to the disk method with the hollow center, but some cases we don't have the hollow center. Okay, we probably just have a complete solid with no hole in the middle, but we have to use the washer method to calculate that. Alright, so let's see our example. Before we get into example 1, I would like to go over the formulas one more time. And about the x-axis, okay, so we are talking about the x-axis as the axis of rotation. So the element is the dx because it's perpendicular to the axis of rotation. So we are going to make sure that we remind ourselves that this is our dx and is perpendicular to the x-axis, which is indicates at our axis of rotation. Okay, and in this unit and in this class, in this lesson, I will not talk about the dy, okay, because this is not a popular formula to use. Excuse me. So all the shape that we are using, this dx is actually very important because we are going to deal with vertical element. Okay, and then you will see later on why we just work with the dx, and the washer method applies to dx most of the time, because take a look at your function here, y2 and y1. So when I indicate y2, it means the function in terms of x. So let's write it down, fx. Okay, so this is also f of x. So that means you are solving for y, and your function is represented by an expression with respect to x. This function is respect to x. So if we are working with a parabola and our function is y equal to, parabola would be x squared minus 3 x plus 2. You see, so it's very hard for you to solve for x. So that's why this formula down here is not that popular to use. Okay, so in this class we just concentrate on the axis of rotation as the x-axis, and we concentrate on the vertical element. So don't forget that with washer method we will have to square the upper function minus the square of the lower function. So let's work with example number 1. Alright, so example number 1, using the washer method, find the volume of the solid generated by the area bounded by the given functions. In this case, we have y equal to 2x and y equal to x squared, and indicate to us that we are working with quadrant 1 and axis of rotation is the x-axis. So the first step is to shade in the area that we are working with. So I'm shading in the area that I'm working with. I also draw the excuse me, the vertical element, and I'm going to show the arrow here to tell everyone that I have to take the upper function minus the lower function. How do I recognize the upper and the lower? Is to take a look at the areas only. Okay, so the area within the area itself, I can see that the straight line y equal to 2x is my upper function, so I'm going to identify that. So this one here, y2 is equal to 2x, okay, and here's y1 is equal to x squared. And in working with quadrant number 1, I know that this is the 0, 0, and I have to find this point of intersection between the parabola and the straight line. So let's write down the formulas that we have to work with. V equal to pi integral from a to b of y2 squared subtract y1 squared, and everything integrate in terms of x. Alright, so let's square our function. So I will take y1 and I square that. So then that means I will have x2 square. So y1 equal to x square, right? So y1 square will be equal to x to the exponent 4 because you are multiplying these two exponents. And for my y2, so y2 equal to 2x. So y2 square will be 2x all of it square. So make sure that you square the 2 as well, and you square the x. So in this case, my y2 square equal to 4x square. So we got this 2 to work with. And now we are going to solve for the point of intersection. Okay, to solve for the point of intersection, I will let these two functions equal to each other. So I will let y2 equal to y1 or y1 equal to y2. So y1 is x squared and y2 is equal to 2x. Okay, so it's very important at this point is that you realize that you are solving for a quadratic equation to get the two solutions for x. So in solving for this as the quadratic equation, you need to bring 2x over to this side. Okay, so the exponent 2 here will tell me that I should have two solutions for x, and it is an incomplete quadratic, therefore I should use factoring to solve for the unknown. So I can factor out x as a common factor. Inside the bracket, I have x minus 2 left. Okay, so now at this point, you can see that x equal to 0 or x minus 2 equal to 0. Okay, so if x minus 2 equal to 0, then x should be equal to 2. Okay, so these are the two values on this as the upper and the lower limit, like on the graph right here. So right here I should have 0, and right here I should have this point is the b. Okay, so I should have 2 and 4, but I just want to indicate right here on the x-axis I should have this equal to 2. Alright, okay, so let's work with our volume. Okay, so I just want to circle this for everyone to make sure that we okay. So volume equal to, okay, so let's do it on this page. So volume equal to pi from 0 to 2 of 4x squared subtract x to the exponent 4 dx, because this one is my y2 square and this one is my y1 square. Okay, so it should be simple now because we already know how to integrate. Okay, so integrating this, I should take 2 at 1, so it's 3, so 4 over 3 x to the exponent 3, and take 4 plus 1, so it should be 1 over 5 multiplied by x to the exponent 5. Add 1 to the exponent divided by the result. Okay, now definite integral from 0 to 2. Apply fundamental theorem. That means pi, we have to multiply by the f of 2, subtract the f of 0. And in checking this statement, or this expression 4 over 3 times x to the exponent 3, I can substitute 0 in here. I can substitute 0 in here as well. Then I realize that f of 0 is actually equal to 0. Okay, so I don't have to write that down. Okay, so the next step is pi multiplied by 4 over 3 times 2 to the exponent 3, subtract 1 over 5 times 2 to the exponent 5. So in this case, I should have this equal to 32 over 3, subtract 32 over 5. Okay, so then in calculating this, I should have 160 divided by 15. I'm taking common denominators, alright? Then subtract 96 divided by 15. Okay, so volume equal to 160 minus 96 divided by 15. So then I should have 64 pi divided by 15 unit raised to the exponent 3. Alright, okay. So let's recap what we have done. Alright, okay. Then I will show you the 3D image of this solid. Okay, so in working with the washer method, it's very much similar to this method. Very much similar to this method. The difference is we are working with two curves, and we have to recognize the upper function and the lower functions. And we have to square the upper function, subtract the lower function, because we are working with two curves for the washer method. Okay, so for this example, I am having a straight line and a parabola. They intersect each other at this point. Okay, the intersection of these two is right here 0 as the quadrant 1, and this here for the 2 on the x-axis, and the axis of rotation is the x-axis, so I should indicate that as well. Okay, so what we do is we let these two functions equal to each other, and then we solve for the point of intersection, so right here. And solving for the point intersection is actually very important. I would like everyone to recall and also to review a bit of algebra. In solving for the point of intersection, we make sure that we are realizing that we are working with a quadratic equation. Okay, so follow the concept of quadratic equation using factoring to solve for the incomplete quadratic. Incomplete quadratic, you are going to have a solution as 0. Okay, so one solution of it has to be equal to 0. And right here, you can make an argument right here. It's a product of these two, right? So in order for a product to be equal to 0, one of this has to be equal to 0. So either x equal to 0 or this whole expression is equal to 0. Therefore, you have two values for x equal to 0 and x is equal to 2. Two solutions for this quadratic equation. And we have 0 and 2 as the 2 as the upper limit, 0 as the lower limit. And then after we square the function that we supposed to, then we substitute into this integrand to integrate. Apply fundamental theorem, and then we get the value that we have. Alright, so let me show you the solid that we are working with. Okay, so the 3D image for this solid would be this one. So I drew the axis for everyone. So right here is our 0, 0. And I should move this a little bit, but roughly is this. So this is your straight line, and this is your parabola. Okay, so you revolve this area about the x-axis, and you generate this shape. So this is only half of it. What about the full one? The full one would look like this. Okay, so this is only a half, and this is the entire shape will turn into this shape right here. Remember that it's kind of curvy inside this, but it's a straight line outside like this. Okay, so this is a straight line. So if I can draw this for everyone right here, I can tell everyone that this one is in fact y equal to 2x. Okay, and then this one is your parabola right here. So this one would be y equal to x squared. Okay, and what do we have next? I actually place the half image on top of the other one, so you see that how I cut that in half right here to show everyone the cross-section area. Okay, so the cross-section area. Alright, so let's take a look at this shape one more time. Okay, alright, thank you everyone, and I will continue with example 2 for this lesson on my video number 2. So this lesson has 3 examples, so it will be divided into 3 videos. Alright, thank you.